In this video, we're going to solve section 10 of the April 2017 exam, one of the 3 long answer questions selected by the class. Here we have a firm that manufactures a commodity at 2 different factories, and we're given a function as the total cost that depends on the 2 quantities, Q1 and Q2, that are being generated by each factory respectively. Now their total objective is to produce 400 units while minimizing production costs. So here we have a constraint. They have to produce 400 units, and we have a goal or an optimization problem, which is to do that while minimizing the production costs. And this is naturally a Lagrange multiplier question, which is perfect for optimizing a function given a constraint. So the first thing I would do here is explicitly write out what the constraint is. They need to produce 400 units, and how do we produce units? Well, we make some in factory 1 and some in factory 2, and that grand total has to add up to 400. We then have the cost function, and going to the nomenclature that we've used in the class, this is what we would call f of Q1 and Q2. And this partnership here is our G of Q1, Q2, and that is equal to some constant K. So we're basically in shape now to execute the method of Lagrange multipliers. Remember, that's building on an alignment between the gradient of f and the gradient of g, so we'll write that out first. They don't have to be equal, but they do have to be parallel, and so we have them equal to each other except with the multiplier, and we also have g of q1 here and q2 has to equal k. You can skip this step if you like and go straight to the x components. The x component of the f of the gradient here is actually not an x component, it's a q1 component. We take the q1 derivative of this, we're going to have 2 q1s plus a q2, and the derivative of this with respect to q1 is 0. So that's the entire q1 component of gradient of f. That's going to equal lambda times the q1 component of g, and g is over here. The q1 component, if we take that derivative, is simply 1. So that's nice and compact. Do the same thing again, but for q2, we will have q1 plus 4 q2s equals lambda times the gradient of g, the q2 component, that is also fortunately just 1. And last but not least, we'll have our constraint q1 plus q2 equals 400. Putting all that together, label our equations here. In this particular case, I think the easiest way to solve it is to set 1 equal to 2 because both of them have equals lambda on one side. And so we get 2 q1s plus a q2 equals q1 plus 4 q2s. And what do we get after that? We can isolate, actually bring the q1 over. We'll simply have 1 q1 left. And then on the other side, we'll have 4 minus 1, we'll have 3 q2s. That can become equation 4. And once we have that equation, we can sub it into the original thing down here for 3. And that'll combine our constraint with our optimal balance of q1, q2. It's actually 3, 1 plus 4. That will give us q1, but that's 3 q2s. Let's use that instead. Plus q2 equals 400. And so that's 4 q2 is 400, or q2 equals 100. Then we can go and find our q1, which is 3 q2s or 300. And so that's going to lead to an optimal production of our optimal cost at 100, 300 of, going back to our original function up here, 100 squared, oops, those are backwards. Q2 is the 100 and Q1 is the 300. So 300 squared plus 300 times 100. And here we can see why we didn't want a large Q2, because there we have 2 Q2 squareds. So 2 times 100 squared plus the 1,000 at the end. If we calculate that out with our calculator, we get a minimum cost of $141,000.